Let's go over the answers to the handout called baseline readings, and then we'll talk about the things that we needed to know to get at those answers, the tools that we needed to have in our mathematical toolbox to get at those answers. All right, so problem number 1. I can't have both on the screen at the same time. I've only got one screen. Oh, well, we'll have to live with it. Problem number the first. What was the answer? 64. 64 what's? Degrees. So for degrees, we're going to use the same degree symbol that we use for temperature. Put a degree, but instead of writing degrees Fahrenheit or degrees Celsius, we just say degrees. Is anybody that's never seen the degree symbol before? That's good. I just wrote one down, so technically you have seen it, and it was before I asked the question. That would be like super terrible way to ask a question, but there it is. Number 2, in question number 2 said, an isosceles triangle contains a 100-degree angle. What are the measures of the other 2 angles? 40. They're both 40 degrees. Very good. How about question number 3? Question number 3, an isosceles triangle contains a 72-degree angle. What are the measures of the other 2 angles? 54. Did anybody get something else? $37, those wouldn't add up right. That's okay. I do that all the time. Does anybody have something else? Yes. 72 and 36. So some of you, how many people put 54 and 54? Most people, right? Especially now because it's written up there. So you're like, oh, yeah, that's what I got. Right? That's how it works. But there's enough space to have another 72-degree angle. So another possible answer would be 72 and 36. Could that have happened in problem number 2? No. Okay, we'll come back to why that is shortly. So loud. Problem number 4. One of the acute angles of a right triangle measures 37 degrees. What is the measure of the other acute angle? So if one acute angle of a right triangle is 37, what's the other one? 53? Great. Number 5, the smaller acute angle of a right triangle measures 1/2 that of the larger acute angle. What are the measures of the acute angle? I have this one. 30 and 60. Sounds good. Number 6, if the measure of the legs of a right triangle are 3 feet and 4 feet, then what is the measure of the hypotenuse? Anyone have it? 5? 5 what's? 5 feet. Because now we're measuring length, so it's going to be 5 feet because we're talking about the hypotenuse, the side of the triangle. Number 7, if the hypotenuse of a right triangle measures 13 meters and one leg measures 5 meters, then what is the measure of the other leg? 12 meters. Sounds good. Number 8, if the 2 legs of a right triangle measure 7 centimeters and 11 centimeters, then what is the measure of the hypotenuse? And then clue, round your answer to the nearest 10. This one doesn't work out. Does anyone have this one? 13.0. Does anybody have the exact length? Because you didn't bring a calculator. Oh, that's just more decimal places in your approximation. No, that's just more decimal places in the approximation. What did you do to get that number? Yes, square root of 170. So when you have the 13.0 or the 13.03 or 13.04, I'm thinking about where that came from. Those are all approximations of the weird number. I should be showing what I'm writing. Square root of 170. This is not how we like to write numbers, but that would be what we call the exact value. So the square root of 170 is the exact value of the length. 13.0 is an approximation to the nearest 10. 13.03 or 13.04 would be an approximation to the nearest 100. So those are approximations. As soon as we grab our calculator and we see all the numbers that it writes and we stop writing numbers, we're approximating. If we want the exact value, we go back one step and write what we asked the calculator for. Cool. Number 9, if two sides of a right triangle measured 9 inches and 12 inches, if two sides of a triangle measured 9 inches and 12 inches, what could the third side measure? Weird things happened in this problem. What did I drop out of this problem from the previous one? If one of the sides is a hypotenuse, did I tell you the hypotenuse? No. Did I tell you that there is a hypotenuse? How did I tell you that I didn't? There might not even be a hypotenuse. What do I have to say for there to be a hypotenuse? Yeah. I've got a triangle. So how do we know what does the hypotenuse have to have? So I have a triangle with a hypotenuse, what has to be there? I need a right angle. I need a specific kind of triangle. I need a right triangle. I didn't say there's a right triangle. So we don't have a hypotenuse. So this problem is very different than the other one. Does anybody have something that the third side could measure? How much? 15. Anything else? 15 works. Anything else? Yes. How much? Sure. It could be a right triangle. I mean, about that approximately one of the legs. Anything else? Why are so many answers working? I know that was only like 2, but probability-wise, it'd be like 40 different answers. I might have to come up with them all, but it could be like 40 different answers. So we'll think about that. While we're thinking about this, let's think about the tools that we need to answer each of these questions. So clearly we come here with some math knowledge, geometry, some algebra, maybe some trigonometry even. What's one of the tools that we need to answer these questions? What did we need to know to get through these questions? Yes. Pythagorean theorem. Once we got down to these sides down here, we needed to know the Pythagorean theorem. Cool. The Pythagorean theorem is one of the tools that we needed to have in our toolbox. What says the Pythagorean theorem? How do we most often remember the Pythagorean theorem? Perfect. A squared plus B squared equals C squared. That is the modern way to remember the Pythagorean theorem. What is it about A, B, and C? Which one is the one that needs a name? Which one is C? The C has to be the hypotenuse. So this is like an agreement. We've all agreed that this is how we're going to remember the Pythagorean theorem. It goes along with C being the hypotenuse. We never say that part. We just say A squared plus B squared equals C squared, and they're like, yep, Pythagorean theorem. And no one ever says, what if A is the hypotenuse? Because it's like, oh, come on, man, play along. We've all agreed that C is going to be the hypotenuse. What we don't appreciate is, so C is a hypotenuse. What we don't appreciate is that we get to say a squared plus b squared equals c squared. Pythagoras did not get to say, I know for a fact that Pythagoras never said a squared plus b squared plus c squared. Because he didn't get to have algebra. He didn't have algebra to work out, to abbreviate his math stuff. He had to be like all the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. I don't think he said it in English, but I had to translate that part. But I know he didn't say a squared plus b squared equals c squared because he didn't have algebra at the time. So lucky us. It's kind of weird for me to say lucky us when I'm talking about algebra. We get to have algebra. And like, oh, no, we don't get to have algebra. We have to have algebra. And we're still mad about it. I don't know, some people are. So yeah, the Pythagorean theorem is one of the things that we needed to solve these problems. What's another thing that we needed to know to solve these problems? What's the one we needed right off the bat in problem number 1? What's that? Yes. I'm sorry. Oh, we don't need sine cosine. What do we need for that first problem? Right. What did you actually calculate? Awesome. We needed to know that the sum of the angles in any triangle is 180 degrees. So that's one of the tools that we had in our toolbox. So that's one of the tools that we have in our toolbox for solving problems concerning triangles. The sum of the angles in a triangle is 180 degrees. How did that change when we move on to problem number 2? What else do we have to know in problem number 2? Because I only told you one of the angles. I gave you 100 degrees instead. I gave you one angle instead of 2 angles. What do we have to know in problem number 2? What was different? Long. What was different when we switched to problem number 2? There's more than just some of the angles. Yes. 2 angles are equal. What told us that 2 angles were equal? This is an isosceles triangle. So the word, when we say a triangle is an isosceles triangle, that means 2 of the angles are equal. Oops. So we needed to, once we see that this is an isosceles triangle, that means that we have 2 equal angles. So with 180 degrees total, 100 taken up by one of the angles, that leaves 80 degrees to be split amongst 2 equal angles. I guess we also need to know how to divide by 2. But that's the tool that we need. Problem 3 was the same. What we wanted to notice in problem number 3 that's specific to this problem is that we can, although we can only fit one 100-degree angle in a triangle, we've only got 180 to go around. We can fit 2 72-degree angles in a triangle. So if one of them is 72, it could be that the other one is a 72 as well. Probability-wise, the most common thing for people to pick is going to be 54. All right. In problem number 4, what did we need to know? What was the new thing in problem number 4? Yes. Yep. In this case, we have a right triangle. That means one of the angles is 90 degrees. One of the angles is a corner, a right angle. A right triangle has a 90-degree angle. A right triangle has a right angle. So that's what we need for that one. That's also needed for problem number 5. So problem 4 and 5 are both, there's 180 degrees total, 90 are taken up by the right angle. What are the other 2? And then in problem 6, we needed the Pythagorean theorem. And in problem 7, we just needed to rearrange the Pythagorean theorem. And then problem number 8, we still need the Pythagorean theorem. And then in problem 9, we haven't really talked about it. Here are the tools that we needed to get through these problems. The main things that we needed to know are the sum of the angles of the triangle is 180 degrees, and we needed to know the Pythagorean theorem. We also needed to know some stuff about isosceles triangles. That helped us use the primary tool. Sum of the angles of a triangle is 180 degrees. And we had to know the meaning of a right triangle. That means one of the angles is 90 degrees. If we were dropping the Pythagorean theorem, we already knew some stuff about right triangles because Pythagorean theorem specifically works on right triangles. So notice that one of our tools applies to any triangle, and the other tool applies to only right triangles. Any questions? Comments? Is trigonometry super easy? We haven't really done a lot of trigonometry yet. Someone did bring up sine, cosine, and tangent. It's like, oh, I see where this is going. This is heading to sine, cosine, and tangent, isn't it? I'm like, oh, no, yes. That is where we're going to spend most of our time. All right. So notice that we did, this class is normally 2 hours long. I'm not going to go straight 2 hours, straight through for 2 hours. And normally we're going to take a break, but I don't have as much to do for the rest of the day. So I'm just going to push through to mention the last thing, and then we're going to adjourn until Monday. Any questions? So at 2:15, normally we'll take a break right around this time, but I think today we're going to be taking a break not for like 5 or 10 minutes, we're going to be taking a break for several, 5 minutes. We'll all just make it one class. Sometimes we just like 5-day breaks. Here's what we want to notice about the tools that we have. The sum of the angles of the triangle is 180 degrees. This applies to any triangle. That's one thing we want to notice. It goes for any triangle. So this works for any triangle. What we want to notice is that this tool only involves the angles of a triangle. So the sum of the angles in a triangle is 180 degrees. All we're talking about is the angles. We know nothing about the sides. So this tool only has angles. That's a limitation. That tool is only useful for answering questions about angles. Notice that we had to abandon that tool in favor of the Pythagorean theorem once we had questions concerning sides. But notice all those questions using the Pythagorean theorem only involved sides. What this tells us is that we need something that will connect the angles and the sides of a triangle. We need to connect the angles and the sides of a triangle. We need some tools that will connect the sides and the angles. We need tools that involve not just angles, not just sides, but both. We need tools that involve sides and angles. And that's why we have trig functions. The trig functions, the ones that we're going to be using most of the semester, those are tools that we can use that involve sides and angles. trig functions are going to involve sides and angles. We're going to start off looking at trig functions in right triangles. We're going to limit ourselves to right triangles before we start expanding out to using trig functions on any triangle. So we've got to name some parts. I'm going to label the angle down at the bottom. I'm going to say this is angle theta. To make a theta, just like make an O and then just keep going across right through the middle. That's going to be angle theta. Specifically, it's a lowercase theta. Although this is how I write uppercase theta. Now, in this right triangle, one of the sides is a hypotenuse. Which one is the hypotenuse? That's the angly one in this case. The hypotenuse is always opposite the right angle. So the hypotenuse is always opposite the right angle. It's the side of the triangle that is not part of the angle. So if we're standing in this angle and look at and have a hand on each side, we're opposite, the hypotenuse is opposite that angle. So that's what we mean when we say a side is opposite an angle. So we want to name the other two sides in relation to the angle theta. So this vertical leg over here is going to be opposite. And when I refer to the side opposite in a right triangle, I am specifically referring to the angle, the side opposite an angle I'm interested in. If I wanted the angle opposite, if I wanted the side opposite the right angle, I would say hypotenuse. So hypotenuse is opposite the right angle. This side is opposite of theta. That's opposite to theta. Some of you probably might know this one already. Some of you might know this one already. What is the other side going to be called? Adjacent. And how am I going to abbreviate it? It's like you've seen this show before. So the three sides of our right triangle, we're going to have a hypotenuse. Then with respect to one of the angles, we'll call one of the angles opposite and the other one adjacent. And using this, we can define our three most important trig functions. What are the three most important trig functions? Some of you already know. Sine, cosine, and tangent. How many of you were thinking in that order? Is anybody thinking a different order? Is anybody like, no, tangent, cosine, sine? No, everybody always goes sine, cosine, tangent. Because you're all copying off each other. It's just plagiarism, straight up play. I'm just kidding. I want plagiarism in this class. I want everybody like, oh, what's 4 times 5? I want everybody to write 20. That's it. I want the same answer. It's like the opposite message that you get from your English class. Your English class would be like, oh, I'm so mad. Everybody wrote the exact same thing. But in math class, like, oh, everybody wrote the exact same thing. I'm so happy. And they're called mixed messages. And then the schools are called, that's part of the trauma. So our three trig functions, there are more. Our three favorite trig functions are sine, cosine, and tangent. And each one has a three-letter abbreviation. For sine, we write sine. But we can't just write sine by itself. That doesn't mean anything. It has to be sine, and it has to apply to an angle. Sine of theta. Our abbreviation for cosine is cosine. And our abbreviation for tangent is tangent. And the transcript looks weird because I said the abbreviation for tangent is tangent because when we see tan theta like that, we're going to say tangent of theta. We're not going to say tan theta. We don't just read a bread. Okay? Okay. Don't just read the abbreviations. Say what they're abbreviating. Some of you might know what I'm about to write next. What is sine of theta? Some of you know this already. It's okay if you don't. Opposites over hypotenuse. Awesome. What's cosine of theta? Adjacent over hypotenuse. See, some of you have secret math knowledge already. And what's tangent of theta? Opposite over adjacent. So sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. Tangent of theta is opposite over adjacent. This is a rule, just like these are rules, just like the Pythagorean theorem that apply to right triangle. We're talking about hypotenuse. We have to be talking about a right triangle. If hypotenuse is around, you must be talking about a right triangle. Even though tangent of theta is opposite over adjacent, we don't refer to the hypotenuse. There has to be a hypotenuse if opposite is going to mean anything. You just have to remember these three things. You don't have to memorize these three things. You do have to remember them though. Always. Like instantly. No thinking about it. If it takes you 3 minutes to come up with these three things, then you don't know them yet. It's like parallel parking. If it takes you 40 minutes to parallel park, then you can't parallel park. I'm not saying you have to get it on the first try, but you can't be there for like an hour. Hang on, let me try again. If it takes you 50 times, you need more practice. On the upside, if you just did it 50 times, you've got a lot of practice in. So sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. Tangent of theta is opposite over adjacent. You're going to abbreviate this when you're trying to remember it. Sine is opposite over hypotenuse. Leave off theta part. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So you're going to remember SOHCAHPOA. Does anybody know the word that we make out of those? SOHCAHPOA. Has anybody heard of SOHCAHPOA before? I usually don't use SOHCAHPOA because when I was introduced, it was super racist. It's not anymore, but it was when it was told to me, so I'm not going to do it anymore. But SOHCAHPOA. Sine is opposite over hypotenuse. We're just grabbing the first letters. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. If we remember to go in the order sine, cosine, tangent, we can remember OH, AH, OA. Oh, heck, another hour of algebra. So that's one that was given to me. Oh, heck, another hour of algebra. You can use my personal favorite mnemonic device for remembering these. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. That's my favorite. Any questions? Your job this weekend before class next week on Monday is to remember sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. If you're getting sick of hearing me say sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, then it's working. That's how songs get stuck in your head. You hear them a ton of times in a short time span. You don't just hear them once. And I want this song stuck in your head. I want you to be mad at me every time I say Sine is optional, hypotenuse, cosine is good, so hypotenuse is optional, good. Because I want it to be automatic. Any question? I promise I won't say it again today. But on Monday, what's the first thing I'm gonna be asking? That's my gift. All right, that's gonna do it for today. Welcome back, everybody, or welcome here, everybody. I'll see you all on Monday. This is Monday, Wednesday class. I'll see you all on Monday. Everybody have a good day, and thanks for playing.